quantum computing, it seems like it's always being talked about these days as this futuristic thing. Supercomputers solving these impossible problems.
Right.
But what if we're closer than we think?
Oh, yeah.
Like actually on the verge of it becoming reality.
Yeah, for sure.
And we're talking about a jump in power that's...
huge.
Yeah, like, I don't even know, like going from an abacus to a modern supercomputer.
Absolutely.
Like that kind of leap. And that's kind of what we're going to be looking at today. A new development that's making big waves in the quantum world.
Awesome. Can't wait.
Yeah, so our focus today is an article from scitechdaily.com. It's called Groundbreaking 8-Photon Qubit Chip Accelerates Quantum Computing.
Okay.
And it was just published a couple days ago, November 16th, 2024.
Wow, very recent.
Yeah, very, very recent. And it details a truly groundbreaking achievement by researchers in South Korea. They developed this 8-photon qubit chip, and it's really pushing the boundaries of what we thought was possible.
I see, yeah.
With quantum computing. Now, I know photon might sound kind of intimidating,
right?
But really it just means a particle of light.
Okay.
So that's all it is. But what I find fascinating is that this chip actually uses these photons to perform calculations. So can you tell us a bit more about that? Why photons? Why are they being chosen for this?
Well, they have some really intriguing advantages when it comes to building quantum computers.
Okay.
One of the big ones is the temperature.
Okay.
Some other quantum computing technologies, they need these super low temperatures.
Yeah.
Like insanely low.
Yeah.
So you need these massive cooling systems. But photons, they're fine at room temperature.
So that seems like a huge plus, right? Not only is it just practical, but it could potentially even make quantum computing more accessible.
Absolutely, yeah. Much more accessible.
I'm aligned.
For sure. And then you also have the issue of errors. You see, quantum systems are really delicate. They're prone to errors, all this environmental noise. But photons, because they don't interact with their surroundings as much.
Right.
They're inherently more stable, less susceptible to error.
So they're kind of like...
more reliable.
Yeah, more reliable. Like,
workhorses.
Yeah, like they're in it for the long haul.
Yeah.
Not as bothered by everything around them.
Exactly.
Okay. So now let's talk about entanglement, this almost mystical thing that's at the heart of quantum computing. It's almost like, you've got these qubits, these photons that are linked,
right,
but in this invisible way, even when they're physically separated. And that's what gives quantum computers all this power. Yeah,
exactly. And this chip, it's actually achieved 6-qubit entanglement.
Okay.
Which is a record for silicon-based photonic chips.
Wow. Okay. So we've got silicon-based photonic chips, 6-qubit entanglement.
Right.
Can we unpack that a little bit?
Sure.
Break it down. What does this mean for building powerful quantum computers?
It's a big step.
Okay.
A big step towards creating more powerful and more complex quantum computers.
Okay.
You see, using light on silicon chips, this silicon photonics, it offers a way to scale up the number of qubits.
Right.
And that's essential for tackling those complex problems, those real-world problems. And so 6-qubit entanglement on this platform, it shows just how much progress is being made.
So it's not just entangling more qubits, it's about doing it on a platform that can scale up.
Exactly. Think of it like building a network.
Okay.
A massive one, all interconnected. You wouldn't want to use parts that are hard to make.
Right.
Silicon photonics, it offers that path to building larger systems more efficiently.
That makes a lot of sense. So we've got these photons.
Yep.
They're zipping around.
Yeah, on the chip.
On the silicon chip. They're entangled in this way that, like, it's hard to wrap your head around. It's like, it makes no sense.
Yeah, it's wild.
But how does the chip actually work?
Well, so you got to think of the chip like a city for photons.
Okay.
A miniature city. And it has 8 photonic sources.
Okay.
And these are kind of like the starting points.
Right.
Where these single photons, representing qubits, are generated.
Okay.
And then you've got these intricate networks, they're called waveguides, like tiny, tiny optical fibers.
Okay.
Etched right into the chip. And they're kind of like the roads that the photons travel along. And then to control the flow of traffic, you've got optical switches.
So like traffic signals.
Exactly.
Oh, okay.
Guiding the photons along specific paths.
Wow. It's like a dance of light, but choreographed.
Yeah, you got it.
But very complex.
Yeah. And to make sense of the dance, we need to be able to read what happens.
Okay.
Right? Read the outcome. And that's where single photon detectors come in.
Okay.
These are super sensitive devices that can detect individual photons. And by measuring the state of the photons at the end of their journey,
Right.
we can decipher the results of the computation.
It's pretty amazing when you think about it.
It is, yeah.
The complexity, the precision.
It is, yeah.
It's mind-blowing.
And the team, they've got some big plans.
Okay.
They want to make 16 qubit chips
Wow.
this year
Okay.
and eventually get to 32 qubits.
So they're going for it.
Oh, yeah.
Hmm.
This is all about scalability
Mhm.
and making quantum computing practical.
So scaling up the number of qubits, that seems to be like the big thing.
It is.
Everyone's after that. Why is that such a crucial goal?
Well, think about it. Imagine trying to solve a complicated math problem
Okay.
on a tiny notepad
Okay.
versus having a massive whiteboard.
Right. Yeah.
The more qubits you have, the more complex the problems you can tackle.
So it's not just about bigger chips.
No.
It's about like expanding the possibilities
Exactly.
of what we can even do with quantum computing.
Exactly. That's it. And this team, they're not stopping there.
Oh.
They want to use this tech for a cloud-based quantum computing service.
What?
Yeah. Imagine researchers, businesses all over the world,
Yeah.
all having access to this through the cloud.
So that could really democratize things, right?
Absolutely.
And really spur innovation in like almost every field.
Yeah.
But, I mean, there's got to be challenges, right?
Yes, there are.
I mean, even with all this progress.
Big time. I mean, this is cutting-edge technology. There are always going to be challenges, especially in a field as complex as quantum computing.
Yeah.
One of the big ones, those errors.
Right. The noise.
The noise, yeah. Keeping those qubits stable,
Right.
it's tough. Like trying to conduct this delicate symphony with all this static.
Yeah.
And researchers they're always trying to find ways to shield these qubits from all that noise, make sure those computations are accurate.
But they're making progress.
Oh, huge progress.
Yeah.
Yeah, and this chip, this 8-photon qubit chip. Yeah.
From South Korea. It's proof of that.
Yeah.
We're getting closer to that future.
To that future where those seemingly impossible calculations from quantum computing become reality.
That's it.
Yeah, it really is an exciting time. But I think before we get too carried away
Yeah.
with all the possibilities, let's take a step back
Yeah.
and look at some of the challenges and maybe some pitfalls
Okay.
that come with this technology. And that's what we'll be doing in part 2.
Looking forward to it. So welcome back to our deep dive into the quantum realm.
Yeah.
We looked at this 8-photon qubit chip
Right?
in part 1 and all this amazing potential.
Mm-hmm.
But it's like they say, right?
Yeah.
With great power comes great responsibility.
Exactly. And I think that's a really important point to make here because on the one hand,
Yeah.
we're talking about, potentially revolutionizing medicine, materials,
Yeah.
finance, you name it. But
Yeah,
then
yes.
there's this whole other side to it.
Yeah. Where it's like, okay, what about security,
Right.
misuse, even disruption on a scale we've never seen before?
Right.
It's a little unsettling.
It is. It's definitely uncharted territory.
Yeah.
So maybe let's start with that.
Okay.
The potential for disruption. Take cryptography, for example.
Okay.
A lot of our digital world relies on encryption algorithms
Right.
that would take, normal computers, classical computers, millennia to crack.
Okay.
But a quantum computer,
Yeah.
with its speed, it could potentially break those codes
Oh, wow.
in a matter of days or even hours.
So then everything we rely on, for security,
Yeah, think about it.
our bank accounts, communications, everything could be vulnerable.
It's a concern, definitely. And it goes beyond individuals, too.
Oh, right.
National security, government secrets, the financial markets.
Yeah, that's a lot to think about.
It is.
So what can we do? I mean, is it already too late?
No, not at all.
Right.
There are researchers are already working on new encryption methods,
Okay.
quantum-resistant ones.
Oh, okay.
So it's a race for sure,
Mm-hmm.
but it's essential to stay ahead of the curve.
Right. Yeah. It's almost like we're building this fortress, but at the same time, we have to figure out how to make it even stronger.
Exactly. Before someone figures out how to break in.
Yeah.
But
Yeah.
let's not just focus on the negatives.
Right.
Quantum computing has this incredible potential for good too.
Mm-hmm.
So let's shift gears a bit. Talk about medicine, for example.
Okay.
Imagine being able to design drugs
Mm-hmm.
with this level of precision and speed. It's mind-blowing. We could tailor treatments
Wow.
to each patient, target diseases at the source.
That sounds like something out of science fiction.
It does, but it's becoming more and more real. Quantum computers could help us understand these complex biological processes at a level of detail we never thought possible.
So breakthroughs in drug discovery, gene editing, potentially even new therapies we haven't even thought of yet.
Yeah, and it's not just about treatment. It's also about diagnostics.
Oh, right.
Finding health problems early.
That's huge.
It is, because early detection, often that's the key to successful treatment.
Yeah, for sure. So it's not just medicine.
No, not at all. Quantum computing could transform so many industries. Material science.
Okay.
Think about it. Designing materials with specific properties. Superconductivity, incredible strength, all by simulating how atoms and molecules behave.
At the quantum level.
At the quantum level,
Exactly.
So lighter materials, stronger materials, more efficient materials.
So like skyscrapers that are super strong but really lightweight.
Yeah, or batteries that last for weeks.
On a single charge.
On a single charge, exactly.
Yeah.
And we can't forget about AI.
Right, artificial intelligence.
Yeah, quantum computers could speed up all those machine learning algorithms. So AI systems that learn faster, adapt faster.
Wow.
Leading to breakthroughs in natural language processing, computer vision, robotics.
So AI, that's not just, faster and more efficient, but also more intuitive.
Exactly. More human-like. And as these systems get more powerful, we could use them to tackle some of the world's biggest problems. Climate change, poverty.
It's like we're giving AI this superpower to analyze all this data and come up with solutions that we couldn't even imagine.
That's a great way to put it. But we have to remember, quantum computing, it's still early days.
Right.
There are hurdles, big technical hurdles. And one of the biggest, those errors.
Right.
The noise. Quantum systems, they're incredibly sensitive. It's hard to keep those quantum states stable. It's like trying to build a house of cards on a windy day.
Yeah.
One gust.
Yeah.
And it's all over. Researchers are working on it, but it's a constant battle.
Yeah. And it's not just the technical challenges, right? There's also the ethical side of things, the societal implications.
Absolutely, yeah. As quantum computing gets more powerful, we need to think about who have access to it.
Right.
And how it's being used.
We have to make sure it's developed responsibly.
Exactly. Ethically. Yeah. In a way that benefits everyone.
Yeah.
It's about having these open conversations about the risks and the rewards, thinking about privacy, security, even job displacement.
Right, because certain jobs might just become automated.
Yeah. It's a powerful tool, one that can shape the future. And it's up to us to decide how we use it.
It's a big responsibility.
It is. But for now, let's focus on something a little more concrete.
Okay.
In part 3, we're going to explore the latest advancements. New types of qubits, new algorithms.
So we're going even deeper into the quantum frontier.
We are. Stay tuned.
So welcome back to our final deep dive into the quantum world.
It's been quite a journey.
It has, and we've covered a lot.
Way up.
We talked about that chip.
The 8-photon one.
Yeah, the 8-photon one.
Right.
The potential impacts on society, both good and bad. But now it's time to kind of look ahead to the future of this whole technology.
The future of quantum.
Yeah, and it's evolving so quickly.
It is. It's really exciting to see where things are headed.
It is, and we've talked a lot about photons.
Right, as qubits.
Yeah, and how they're being used to create these qubits.
Yeah.
But there are other approaches out there.
Oh, absolutely. It's not just photons.
Yeah, other ways to actually make these qubits.
Yeah, there are lots of different ways to create qubits.
Okay.
And researchers are exploring a lot of different paths.
So it's not just one horse race.
No, not at all.
Yeah.
And each approach has its pros and cons.
Okay.
But one of the most promising ones right now is superconducting qubits.
Okay.
And they use this thing called superconductivity, where basically the electrical resistance just vanishes.
Oh, wow.
At these super low temperatures.
So the electrons are just flowing freely.
Totally freely. Zero resistance.
That's incredible.
It is. And that makes them really controllable.
Okay.
Which is really important for building those complex quantum circuits. And they've shown some good scalability too.
Okay.
So they're really good candidates for building these larger, more powerful.
So they're definitely in the running.
Oh yeah, for sure.
Okay. But you said there are other approaches too.
Yeah, there are. There's another really interesting one called trapped ion qubits.
Trapped ion qubits.
Yeah, and these use individual atoms that are trapped and controlled using electromagnetic fields.
Oh, wow.
And the great thing about them is that they have these long coherence times.
Okay.
Meaning they can hold their quantum states for a really long time.
So that's super important for doing those calculations.
It's critical. It's essential.
It's like we're suspending these atoms in midair.
Yeah. It's kind of like
and then just, manipulating them with this insane precision.
Yeah, it's like a high-tech juggling act.
Wow.
But with atoms.
That's amazing.
Yeah.
But I know there are even more kind of, I don't know, exotic approaches out there.
There are. There's one that's getting a lot of buzz right now. It's called topological qubits.
Topological qubits.
Yeah, and these are based on braiding particles called anyons.
Anyons.
Yeah, and what makes them so interesting is their potential for robustness.
Robustness.
Yeah. They're thought to be really, really resistant to errors.
Oh.
Which is a big problem in quantum computing.
Right, yeah.
So they're great candidates for building these fault tolerant.
So they're like the armored vehicles of the quantum world.
Yeah, that's a great way to put it. And all this research on all these different types of qubits, it just shows that, quantum computing is still in its early stages.
Yeah, it's still evolving.
It's a very dynamic field.
Yeah.
And there's so much more to discover.
Right. And it's not just the hardware, right?
No, absolutely not. You could have the best hardware in the world, but you also need
the software.
The software, exactly. Yeah. You need the algorithms.
Well, the algorithms
to harness that power.
Yeah.
And that's where quantum algorithms come in.
Okay. Yeah.
So these are algorithms that are designed to take advantage of quantum mechanics.
Right.
To solve problems that classical computers just can't handle.
So it's like having a whole new set of tools to work with.
Exactly. A whole new toolbox. And one of the most famous examples is Shor's algorithm.
Okay.
This algorithm can break the encryption.
What
we use for so much of our digital security today.
So that's the one that people are worried about.
It is. It's a big deal for cybersecurity.
Yeah.
But it also shows
the power of quantum computing.
Yeah, the incredible power. And there are other algorithms too, like Grozer's algorithm, which can speed up searches through tons of data. Like imagine you're looking for something in this massive database.
Okay.
Grover's algorithm can find it exponentially faster.
So it's like finding a needle in a haystack, but like way faster.
Exactly. And this has, this has huge implications for so many fields. Database management, drug discovery, even just, searching the internet.
Right, yeah.
And we're really just scratching the surface. There are so many quantum algorithms being developed right now for all sorts of different applications.
Yeah.
From optimization problems to machine learning. It's a really exciting area.
It's mind-blowing to think about all the possibilities.
It is.
It's almost a little daunting too.
It is. But I think, if we're careful, if we consider both the potential and the risks.
Right.
I think quantum computing can help us solve some of our biggest challenges.
Yeah. I mean, imagine a world where we can design new medicines.
Yeah.
In a fraction of the time.
Yeah, or new materials.
New materials.
That revolutionize energy. Or AI that can tackle climate change. It's an amazing future.
It is, but like we've been talking about, it's not guaranteed, right?
Right.
It's really up to us to kind of guide this technology, make sure it's used for good.
Absolutely.
And not for bad.
We have a responsibility as researchers, policymakers, even just as everyday people to really think about these things.
Well, this has been an incredible journey.
It has.
Into the world of quantum computing.
Yeah, it's been a fascinating deep dive.
It has. Thank you for joining us.
Thanks for having me.
As we went on this journey of exploration.
Absolutely.
Into this really fascinating frontier of science.
It's been a pleasure. And as we move forward into this new era of quantum, let's remember to approach it with curiosity, but also caution.
Right.
To ensure that this power it's used to make the world a better place for everyone.
Yeah.